Math 2414, Taylor and Maclaurin series, summary of series to memorize. All right, so we've run across a few series, but as you move forward throughout your math, physics, and engineering career, there are some that you just should flat out know. Now, I will admit that I didn't hit every one of them that you should know, so I'm just going to review the ones that we did do and then list the ones that we didn't do. Excuse me. All right, so let's start with 1 over 1 minus x. That's just the sum of a geometric series, so we can say n equals 0 to infinity of x to the nth power. But for each of these, we also have to know where it converges. Let's go ahead and write this out. This is just 1 plus x squared plus x cubed. And it converges over here. We're going to list the interval of convergence. This converges when x is between -1 and 1, which is equivalent to saying the absolute value of x is less than 1, which makes sense because it's a geometric series, and anytime the ratio's absolute value is less than 1, you get convergence. The next one was sine of x, which is equal to the sum of n equals 0 to infinity of, it was, I'm shooting blanks here. It's driving me crazy. 1 over, -1 to the n. I knew there was something up there. Over 2n plus 1 factorial times x to the 2n plus 1. If you'll recall, when we did the Maclaurin series for sine, all the even powers disappeared and all the odd powers remained. It was an alternating series. And yeah. So this was equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... And of course, I ran into my interval of convergence. But the interval of convergence here is all real numbers. So negative infinity less than x less than infinity, which is actually a correct way to say all real numbers, because all real numbers are greater than negative infinity and also less than positive infinity. For cosine of x, it was the sum n equals 0 to infinity, -1 to the n over, back up. Okay, this is correct. -1 to the n over 2n factorial, x to the 2n power. And when expanded, this is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And this also converged for all real numbers. Oh, I left out a super important one that I should have said before sine and cosine. That would be e to the x. E to the x is the sum from n equals 0 to infinity of 1 over n factorial times x to the n. It's not alternating, and it picks up all the positive integer powers, or all the whole number powers, I should say. And we get 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way forever, and it converges for all real numbers. And you might notice that the power series for sine and the power series for cosine looks like if you put them together, you would get the power series for e to the x. The only problem is both the sine and cosine ones are alternating sums, whereas the e to the x isn't. Is there a way to fix that? Believe it or not, yes. I might show you that if I remember to show you that. But this isn't all of them. We did see the one for inverse tangent or arctangent, but we haven't seen it in a while. It was in a much earlier video in the series. But it was the sum from n equals 0 to infinity of, okay, it was an alternating series, and it was an alternating harmonic series, I believe. I'm reaching back into the deep recesses of my brain, but why do that when I can just go look it up? Shame on you. Where's that list of series to know? There it is. Alternating odd powers, no factorials. Okay, it's what I thought it was. I just hadn't seen it in a while, and I didn't want to put something up here and have to correct it. All right, so it's alternating series. It's odd powers of x. No factorial on the bottom, just the 2n plus 1. Does start out positive, so to the nth power is good up there. And that's equal to, if we put in n equals 0, we get 1. If we put in n equals 1, we get 1/3 x cubed. If we put in n equals 2, we get plus 1/5 x to the 5th. We put in n equals 3, we get minus 1/7 x to the 7th. Yep, looks good. And this does not converge everywhere. This only converges between -1 and 1. So it has its radius of convergence is 1. And those are the ones that we got to. Now there was 1, 2 that we didn't get to. I'm only going to show you one of them. And it kind of is the counterpart of the inverse tangent. It would make a good exercise for you to verify this, but it's for the natural log of 1 plus x. The natural log of 1 plus x is an alternating sum, but I said it was a counterpart to tangent inverse. I was wrong. It's an alternating sum, but it picks up all the powers. Sum n equals 0 to infinity of alternator, so -1 to the n, over n x to the n. Make sure that I got that set up correctly. Yes. And if we were to expand that when n is equal to 0, actually n can't be equal to 0. Do you see why? Should be pretty obvious. You can't have 0 in a denominator. So it starts at 1, but the alternating series does start positively, and right now the first term would be negative, so I need to adjust the alternator. We'll just say n minus 1. We could also say n plus 1. But if we put in n equals 1, we will get 1x. If we put in n equals 2, we'll get -1/2 x squared. Put in n equals 3, we get positive 1/3 x cubed. Put in n equals 4, we get -1/4 x to the 4th. And again, if you're wondering where did this come from, this is an example that I did not get to, but it is one that is super convenient to know. And its interval of convergence is also -1 to 1. So as you move forward, especially you physicists and engineers, I can't stress this enough. The more of these series you have memorized, the better your life will be. Some of them are easier to remember than others. But at the very least, I would know these 4. And then I would add these 2 on top of it. There is one more we didn't get to. I'm not going to go over it right now, but I'll just show you what it is a power series for. It's a power series for 1 plus x to the k power. It's appropriately enough called a binomial series. But the reason I'm leaving it out here is multifold. Number one, I had recorded about 4 takes of the binomial series video. Didn't like any of them. Each of the videos were about half-hour long each, which is part of the reason I didn't like any of them. And finally, after the 4th attempt and failure, I said, you know what? We'll just leave this one out. I would recommend taking a look at it. It basically gives you a way to expand a binomial to a power, even if that power is not a whole number. But for my class, I'm going to leave it out. I may go back in the future and make a video for this, and in which case what I'm saying right now would be moot. But for now, we're going to leave that out. All right, so I would know these series and I would know their intervals of convergence.